This video lecture is about the class discussion of ETech 340. So at first, let's discuss about lecture one. In lecture one, what we learned? We learned about current, charge, voltage. So what's the definition of current? Current is equal to d dt of q. So differentiation of q with respect to time. So q is charge. So what will be the q that? So I have to get this q in full format, not in it's in differential format now. So for that case, I have to do the integration from t0 to t. T0 is the initial time. Integration of I dt. I will be integrated with respect to time. Okay. So what is voltage? Voltage is work done from one point to another point where when a charge is moved from one point to another point. This is voltage. And what is power? Work done in unit time. So d dt of W. So we have another power equation, which is P equal VI equal I square R equal V square R. So this equation, we will use it in DC circuit and also in the AC circuit also. AC circuit also. And let's talk about the law of conservation of energy. So the amount of energy created and amount of energy is changed is equal. So that means the summation of all energy will be 0. So what's about energy? So energy, from the definition of power, we see that power is equal to d dt of W. W is energy. So if we want to get W, we have to integrate power with respect to time. So we integrate power from T0 to T with respect to time. Then we learn about independent and dependent sources. So independent sources are two sources like voltage source and current source. So what about dependent sources? We have 4 dependent sources. Voltage control voltage source, voltage control current source, current control current source, current control voltage source. So we will see the use of this dependent source in lecture 4. So let's go to lecture 2. In lecture 2, so we learned about Ohm's law. Before Ohm's law, let's talk about resistance. So resistance is equal to resistivity times L over A. L is length, A is the area of the conductor, where rho is actually unit resistance. So unit resistance will be different for each individual material. So what Ohm's law says? And voltage in a terminal will be proportional to current. So when current increase, voltage increase, and when current decrease, voltage decrease. So to get a equal expression, we come out with a constant. This constant is R. And for for the case of branch, loop, and node, branch means a device which has 2 terminals, that's called branch. Loop is actually a closed path. Node is the point in a circuit. So B will be equal to L plus N minus 1. Then we learn about Kirchhoff's current law, KCL. So current entering in a node and exiting in a node, sum will be equal to 0. And for Kirchhoff's voltage law, the voltage across a closed loop will be 0. Then we learn about Y delta conversion. So now nodal analysis. In lecture 3, we learn about nodal analysis. In nodal analysis, we apply KCL. Then we learn about mesh analysis. In mesh analysis, we apply KVL. So nodal analysis, mesh analysis, and superposition theorem and source transformation can be done to linear circuit. What's the linear circuit? We can express a linear circuit in this format, KIR equal KV. and where K is the linear constant. And then we do we learn about source transformation. In source transformation, what we learn? We learn that we can change the voltage source to current source and current source to voltage source. For if we want to change the voltage source to current source, then the resistor in series with the voltage source will be parallel with the current source and vice versa. If we want to change the current source to voltage source, then the resistor in parallel with the current source will be in series with the voltage source, transformed voltage source. Then we learn about Thevenin's theorem. So uh, we from Thevenin's theorem we know that V Thevenin is actually the open circuit voltage across the load resistor, and R Thevenin is actually the input resistance except the load resistor. So this is for the normal circuit. So what will happen for a circuit which has a dependent source? For that case, we have to follow these 3 steps. At first, we have to turn off all independent source. Then we apply a voltage source V0 at terminal AB. Terminal AB is the terminal where I remove the load resistance. Then we will determine the resulting current I0. So why we want to determine the resulting current? From I0 we can determine the R Thevenin. That's why after I0 we will calculate R Thevenin from Ohm's law. So let's do an example. So I have this circuit. This is 2Vx over here, and this circuit in figure 1. So we want to know the load current and load voltage across terminal AB. So we see that actually there is a dependent source, voltage dependent source, 2Vx. So this 2Vx is dependent on the voltage Vx. So what should we do? At first, we have to remove all the independent source. So we remove this 5 ampere current source, and then the circuit looks like this, figure 2. Figure 2, then we apply mesh current over there. So we apply mesh current in mesh 1 and we get this expression, but we see that for minus 4I2 is equal to Vx. This Vx, Vx equal I1 minus I2. Hence I1 equal minus 3I2. 3I2. So from loop 2 and 3, loop this 2 and 3, we get 2 expression from KVL solving. We get I3 equal to minus 1/6 ampere. But I3 is just opposite of I0. So we can write that I0 is minus I3, then I0 will become 1/6 ampere. Hence R Thevenin will be, as we took V0 as 1 volt over here, V0 equal 1 volt over here, then R Thevenin will be 6 ohm. To get the V Thevenin, we have to take another circuit, this figure 3 circuit over here. This is mesh 1, this is mesh 2, and this is mesh 3. So if we look at the mesh, I1 equal to actually 5 ampere. So then we apply KVL in mesh 1 and we get this expression. But we see that for I1 minus I2 equal Vx, solving this, I2 become 10/3. Then V Thevenin will be equal 6I2. How it is 6I2? Because we will get the same voltage across AB terminal and across this terminal over here, across the 6 ohm resistor. That's why it's 6I2. I2 current is flowing through the 6 ohm resistor. So if we get the value of I2, then we get the value of V Thevenin. So that's why we get it over here. So this is one solution of Thevenin's theorems with the dependent source. And this is the final circuit of the Thevenin theorem. This is VThevenin and this is the RThevenin. Okay, now Norton's theorem. Norton theorems. In Norton theorems, we calculate R Norton, which is equal to R Thevenin. And instead of VThevenin, we calculate Norton current, which is basically actually the short circuit current across the load terminal. So we can express IN equal V Thevenin over R Thevenin. So R Thevenin will be open circuit over I short circuit equal R. Then we learn about the maximum power transfer theorem. So we can transfer maximum power when our load resistance is equal to the Thevenin resistance, then we can transfer maximum power to the load. So in lecture 5, we learn about capacitor. Capacitor opposes the change of voltage. So, and it stored charges. So charge Q equals C times V, where C is actually the capacitance, which will be epsilon A over T. Epsilon is the permittivity. Permittivity mm, depends on the material, its material property. Permittivity measures the ability to store charges to a material. So that's called permittivity. And from lecture 1, we already know that I equal d dt of Q, and current across a capacitor will be I equals C times d dt of V. Then if I want to get the value of V, what will be the formula? What will be the expression for that? So we have to integrate this dV. So if we do that, we integrate this dV, then that becomes V in V with the with the function of t. Then I over C is the capacitance. We integrate over T0 to T. We integrate I with respect to tau. Tau is actually time constant, plus VT0. VT0 is actually the uh, mm, previously stored charge over here. Sometimes it may be 0. So for the case of power in a capacitor, we will apply P equal VI formula. Then CV D is C times V times d dt of P. And what's about the energy? It will be half CV square or Q square over 2C. So what will be the series capacitance? For series capacitor, it will be just like the resistor in parallel, and for parallel capacitor, it will be like resistor in series. And inductor opposes the change of current. So the voltage in the inductor will be L times d dt of I, where L is equal N square mu A over L. Mu is the permeability. So permeability measures how easily a material can support the formation of a magnetic field, where permittivity measures a material's ability to store electrical potential energy within it. So this is in lecture 5 is about capacitor and inductor. So let's go to lecture 6. Lecture 6 is about first order circuit. So let's talk about RC circuit, source free RC circuit. So this circuit is a source free RC circuit where initial voltage V0 is V0, and initial energy is half C V0 square. And if we apply KCL in this circuit, IC plus IR equals 0, then if we express IC and IR, then C d dt of V plus V over R equals 0. Then we do a little bit of math. We divide the both side of the equation with C, and we come up to this. Then we take this part in right side, and V at the bottom of dV. Then we integrate this part, then it's become ln v equal minus 1 over rc times t. We integrate this t over here. So if we transfer this ln in the right hand side, then it's become v0 times x exponential minus t over rc. Tau is time constant, rc. So time constant means this is the time the capacitor will need to fully charged. Then after that time, after this time tau, the capacitor will discharge. So then we can write this formula in this fashion. And what's about IRT? That will be just applying Ohm's formula over there. So just applying Ohm's formula divided by R, we will get the current. And what's about power? VI or V square R. So if we square this part, then V0 square exponential minus 2t over tau. And what about energy? It will be half CV square, where half CV square, half CV square, because if we integrate this, we will come up with these two terms. That's why this term is over here. Okay. So let's talk about source-free RL circuit. So this is a source-free RL circuit over here. So for initial condition, we have initial current I0, then initial energy of Li0 square. If we apply KVL in this circuit, VL plus VI will be equal to 0, then we express VL and VR in this format. Then we do a little bit of math over here to express it in calculus format. So we express it in this way. Then we integrate di over I from I0 to IT, and the right side from 0 to t r over L times dt. So if we do the integration, then it will be ln IT over I0 and minus RT over L. Then if we take this ln to right hand side, then we come out with I0 times exponential minus RT over L. Here our time constant is L over R. If we apply this tau over here, then my current equation will be just like this. So how about the voltage? Voltage will be equal to I times R. Just applying this formula over here. And how about power? Apply VI formula over here, then we come out with this and this expression. And if we integrate integrate this expression, then we come out with this expression. Now let's talk about the singularity function. Singularity function is a function. This is a positive singularity function. When t is less than 0, singularity function will be 0, and when t is greater than 0, singularity function value will be 1. So this is positive singularity function. How about the negative singularity function? When t is less than 0, negative singularity function will be 1, and when t is greater than 0, it will be 0. So let's talk about the step response of RC circuit. The step response of is the response of the circuit due to a sudden application of a DC voltage or current source. So we apply this DC voltage over here, then we have a switching mechanism over here. So at time t0, this switch will be closed. Then it becomes just like this. Okay, so for initial condition, we have initial charge V0. Then we apply KCL in this circuit over here. Then we come up with this, and ut is our unit function over here. So when t is greater than 0, then unit function becomes 1. Then we can write just like this. Then we do a little bit of math and integration on both sides. And after integration and math, we come out with this. So this is the step response of a RC circuit. So what is this actual VS actually? VS is the VS is the source voltage, and V0 is the initial voltage minus VS, the source voltage, times exponential T minus over tau. So for a step response of a RC circuit, what we see when T is less than 0, output is only V0. When T is greater than 0, the output will be this expression. And when V0 is 0, then this will be 0. And we come out with this expression when T is greater than 0. Okay. So we have Vt. So we have It. So we will just differentiate this expression, then we will get It times C. So it's become just like this. Tau, we break tau into RC, then C and C cancel out, with remain with R. So this becomes just like this. So what will be the complete response of that circuit actually? Step response is actually we are attaching a DC source across the circuit. That's step response. What will be the complete response? Step response is the transient response, and there will be also a steady state response. So after some time constant, we will get the steady state response. So we will have two response at a time: temporary response and permanent response. And transient response or step response, or we also call them at natural response, and forced response is actually comes from the independent source, and it will be in the permanent response. So here we call Vt plus VSS. So VSS is my actually permanent response or forced response with the independent source. Vt is the transient response or temporary response. So it will be V0 minus Vs times exponential minus T over tau plus Vs. So this part is temporary response, and this part is steady state response. So transient response is the response the this circuit response will die out with time. When it will die out, so after some several time constant, this response will die out. So steady state response is the behavior of the circuit a long time after an external excitation is applied. So that means this external excitation is actually this DC sources. So this is our complete response expression. Okay, let's look at the step response of a RL circuit. So it will be same for a RL circuit. I will be equal to IT plus IS. So IT is the temporary response, IS is the steady state response. For IT, we can express in this way: A times exponential minus T over tau, where tau is equal to L over R, and ISS is VS over R. So we can write I in this formula. So we have also the initial current for RL circuit. So if we solve for that, when t equal to 0, then I0 will be equal to A plus Vs over R. Then our total expression will be just like this. Vs over R plus I0 minus Vs over R. So I0 is our initial response, and Vs over R, what is this response actually? This is the steady state response. Steady state response times exponential minus T over tau. So this infinity plus I0 minus I infinity times exponential minus T over tau. If I0 is 0, then the expression will be just like this. So this is the step response of a RL circuit. So this is the end of lecture 6. So let's move on lecture 7. So lecture 7 is about RLC circuit, the second order circuit. So for initial and final value, for a capacitor, we will have initial voltage, and for an inductor, we will have initial current. So what will happen if we have source-free series RLC circuit? Then initial voltage V0 will be just like this expression, V0, V0, and I0 will be this I0. If we apply KVL in this circuit, source-free RLC circuit, series RLC circuit, so it will be just like this. Then we do a little bit of math to get the second order expression. And then we apply initial value over here. Initial value over here. Then we took the solution, or as we want to get the solution of current, we took a assumed solution, I equal this solution. Then we apply this solution over this formula over there, over this formula over here, and it becomes just like this. Then we separate A times exponential st, then we come out with this. So this part is zero, this part will be zero. Why? Because we already take this one as a solution. So if we put this part in this formula, then this will be zero. So it's a solution of this whole expression. So now we have to think about this part. Actually, we have to solve this part. If we want to get the solution of this part, this part is actually the quadratic equation known as the characteristic equation of the differential equation. So if we solve this, we will get 2 root s square, as this is s square. So s1 will be just like this, and s2 will be just like this. So this part we express as alpha, and this part we express as alpha and omega. So where S1, S2 will be just like this, and where alpha will be equal to R over 2 times L, and omega 0 will be equal to 1 over root over LC. So S1, S2 is known as natural frequency, which unit is Napier per second. Omega 0 is resonant frequency, and unit is rate per second. And alpha is Napier frequency or damping factor, known as damping factor. Unit is Napier per second. And if we put the value of alpha and omega 0 over here, it will be just like this. Then we are getting I1s A times exponential S1t, and I2s A2 times exponential S2t. So in total current will be A1, will be this expression. Then we have 3 scenarios over here. As we have capacitor and inductor in a circuit, inductor in a circuit. So what will happen? So capacitor will oppose the change of voltage, and inductor will oppose the change of current. So because of these two two phenomena, two forceful phenomena, the circuit will experience some vibration. So we will see, for the case of vibration, there will be 3 cases will be there. One will be overdamped when alpha is greater than omega 0. Another will be critically damped when alpha is equal to omega 0. And another will be underdamped when alpha is less than omega 0. So for the case of overdamped, alpha is greater than omega 0, and capacitor will be greater than 4 times L over R square. And expression will be this one. And we see that for the case of overdamped, we see that after getting the maximum value, it becomes steady. So for critically damped, alpha and omega are equal. S1, S2 will be equal minus alpha, and C will be equal 4 times L over R squared. And expression will be A2 plus A1 times T times exponential minus alpha T. For the case of underdamped case, alpha will be less than omega 0, and C will be less than 4L over R squared. So root will be S1 and S2, they will be complex and conjugate. So yeah, they're conjugate of each other. And we have another term. So this is the damping frequency. which will be this formula, omega d equal to root over omega 0 square minus alpha square, natural response. It will be equal to a1 times exponential. So this will be the natural response, natural response for underdamped circuit. So using Euler identity, it will become just like this. Is cos omega d and sine omega d. B1, B2 will be two constants. So what will be source-free parallel RLC circuit? And the underdamped circuit performance, current performance will be just like this. So it will ringing for over a period of time. So let's talk about parallel RLC circuit, source-free parallel RLC circuit. All are parallel over here. Then expression will be just like this. So this is the initial current across the inductor, and V0 is the initial voltage. So if we apply KCL, KCL in the node, so this will be just like this. Then we do some math over here. We differentiate this equation, then differentiation and integration cancel each other, and left with this, and this get and double integration and double differentiation over here. That's why d dt squares of v. So it becomes just like this. Then we see the same formula just like this, where we take a I equal one solution, I equal a times exponential minus plus st. So same thing happens over here. Then we remove exponential part and come out with this on the polynomial part over here. And for 2 root s1 and s2, it will be just like this. So they are conjugate of each other. And for the case of parallel, alpha will be 1 over 2 or 2 times r times c, and omega will be same for parallel and series RLC circuit. Okay. So the case overdamped, critically damped, and underdamped will be same as the series RLC circuit. So same expression. Critically damped is a little bit different. For critically damped, it was here it was A2, here it was A1 plus A2 times T. And for underdamped, it's just like this. Their conjugate root is conjugate of each other, and expression is same. So this is the case for source-free case, and these are the performance. So overdamped performance, it gets the saturation or steady state response in a very short time. For critically damped one, it takes a little bit time to get the steady state, and for underdamped, it gives the most of the time to get the steady state current voltage. Okay, so what will be the phenomenon if we attach a independent source across this RLC circuit? So this is for the case of series RLC circuit step response. So this will be just like this one over here. The complete response will be transient response plus steady state response over here. So we know what is steady state response. That is just Vs over here. So for the case of voltage expression, so this is for overdamped, this is for critically damped, and this is for underdamped. And what will be the case for parallel RLC circuit with the step response? We apply KCL over here. And KCL over here, when t equal to 0, it will be just like this. Then we apply this. So it's same formula, we just apply another steady state response over here. So this IS is steady state response. So we are done with the DC circuit part. So let's talk about the AC circuit part over here. So in AC circuit, we apply sinusoidal signal. What is sinusoidal signal? Sinusoidal signal will be either sine or cos signal. So this one is one example of sinusoidal signal over here. This is a sine signal over here, where we express this sine signal Vt as Vm times sine omega t, where Vm is the amplitude, omega is the angular frequency, unit is radian per second. So what is amplitude actually? So this wave starts from this zero, come up to this maximum, then go back to zero. So from here to here, this is called amplitude. So from here to here, this is the amplitude of this VT wave. And the omega is its angular frequency. So what is its time period? So this wave starts from zero, get the maximum, positive maximum, then go back to zero, and it gets the negative maximum, then go back to zero, then it repeats itself. So from here to here, it will be its period. Period will be denoted as capital T, and formula will be 2 pi over omega. Omega. So for the case of a sinusoidal signals, Vt is the transient time plus the time period. For the period, we can express just like this Vt, because after this time period t, this signal will repeat itself. So we can read like Vt, and frequency will be inverse of time period, and angular frequency will be 2 pi times frequency. And if we come to phase, for the phase is the extra angle, the phase difference between two sinusoidal signal. I have V1 over here and V2 over here, and the phase angle is actually this, from here to here. How I get this phase angles? We draw everything here in frequency domain, in omega t domain, and with phase actually. Pi is a phase, 2 pi is a phase, and their phase differences from here to here. So that's how this phase is coming over here. This phi is a phase over here. So this is a trig formula over here. A cos omega t plus b sin omega t. We can write c cos omega t minus theta, where c is the amplitude. The expression of amplitude will be just like this, root over a square plus b square, and the difference between this wave and this wave phase difference will be, we can express in this tan inverse a over b. What we see in what we did it in lab. So this is it. So cos omega t is 90 degree apart from sin omega t, and vice versa. So let's say I have this expression over here. How can I express it? 3 cos omega t minus 4 sin omega t. So plus 3 cos omega t. So this will be over here, plus 3. How about minus 4? Minus 4 will be over here. Then what will be the amplitude of the mixed signal then? It will be root over 4 square plus 3 square. 4 square is 16, and 3 square is 9. 16 plus 9 is 25. Root over 25 is 5. So 5 is my final amplitude after these two mixed signal, times cos. What will be the phase difference between them? Tan inverse a over b. A over b, then tan inverse a over b, that means minus 4 over 3. That if we do the calculation with calculator, angle will be 53.1. So this is the phase difference between them. Okay. So let's talk about phasors, complex number that represent the amplitude and the phase of a sinusoidal wave. So this one is the rectangular format. So I want to express this format in only amplitude and phase. That's the phasor format. So this is my rectangular format, and one another term is J. J is the imaginary number which value is root over -1. Root over -1 is actually imaginary number. It's not a real number. So if we want to express this rectangular format in polar format, then it will be just like this. R is the amplitude and P is the phase difference. And if we want to express it in exponential format, then it will be R times exponential J and J times P. So this is our rectangular form, and this is our polar form, and this is our exponential form. So how can I get the value of R from this rectangular form? Using this formula over here. And how can I get the phase difference from this? Using this tan inverse y over x. And what will be the value of x if we want to apply it in a plane? Then it will be the xy plane, then it will be just like x will be equal to r cos phi, y will be equal to r sin phi. Then we can write in this way. So I have two signals, Z1 and Z2. If I add these two signals, what will happen actually? I add the real part together, x1 plus x2, and I add the imaginary part together, J times y1 plus y2. So how about the subtraction of a rectangular format? So it will be just like this. Subtraction of the real part, subtraction of the imaginary part. How about multiplication? For the case of multiplication, two signals amplitude will be multiplied and their phase difference will be in addition. So for what about division, Z1 over Z2, then their amplitude will be divided R1 over R2 and their angle will be subtracted. And reciprocal of a rectangular signal will be just like this. So their angle will be just a minus. And how about square root of a rectangular signal? So it will be just like the root of the amplitude and half of their phase. So what is complex conjugate? Opposite of the complex signal. So Z conjugate will be x minus jy. And then their phase will be in negative and their exponential sign will be negative. And this is the Euler identities we already know. And cos theta part is the real part of the j theta, and sin theta part is the imaginary part of ej theta. So this is our time domain representation of the signal, and this is the phasor domain representation of the signal. Okay. So let's talk about leading and lagging. So lagging will be minus theta and leading will be plus phi. So plus phi. This will be just like this. So if we express this voltage in sinusoidal format, then it will be just like this. We can write in exponential format, and this is the phasor format. Im is not imaginary, it's the amplitude of the signal I. Okay, and then we can write in this way, applying the Ohm's formula over here, and ICV is C dt of V, this V over here, and if we do the differentiation, we come up this, then we get the value of V from over here. So impedance. So in AC circuit, in DC circuit, we have only resistance, but for AC circuit, we have real resistance and imaginary resistance. Imaginary resistance come from capacitor and inductor. Capacitor and inductor. So if we apply DC, we will not get this imaginary resistance. But if we apply AC, we are getting this imaginary resistance, which is called reactance. And reactance is denoted as X. So impedance is the sum of real resistance and imaginary resistance, sum of resistance and reactance. So it's expressed in this format. This is the polar format over here. And what will be the amplitude? So this will be the amplitude, and the phase difference will be just like this. And the real part will be is amplitude times cos theta. Imaginary part reactance will be amplitude times sin theta. So what is admittance? It is the reverse of impedance. So that's actually I have conductance and susceptance. Susceptance is actually the imaginary conductance of capacitor and inductors from there. So we can express in this way. So if we express in this way, this is impedance, right? Impedance in the denominator is in the complex format. But we want in the real format. So that's why we multiply the conjugate of this complex number in denominator and numerator and come out with this real part over here. So here my conductance is this part and susceptance is this part. We can apply Kirchhoff's law, KVL, KCL in also in the frequency domain, and we can also apply Y delta conversion in frequency domain. So let's talk about AC circuit from lecture 8. So in AC circuit, we can apply nodal analysis, mesh analysis, superposition theorem, and Thevenin's theorem. So let's talk about power. So this is one power signal over here. So this part is half of VMIN. So we apply P equal VI formula over here, and this part is half of VMIN cos theta V minus theta I. So this theta V is actually the angle of voltage, and theta is the angle of the current. So this is the phase difference over here. So instantaneous power means the power when you measure the power at a time, at that moment that power is the instantaneous power. So we apply P equal VI formula over here, but we cos terms over here. And if we apply trig formula cos A cos B, then this is just like this. So we apply this trig formula over here. So it's become just like this. So average power is the instantaneous power over one period. So one period. So from here to here, this is one period over here. So this will be the average power actually. This part is the average power. So 1 over T, T is the capital T is the average period from integrate from 0 to T, PT dt. Then we integrate this part. So we can also express without integration this way, half of real V I conjugate. So it will be just like this. So for the case of maximum average power transfer for what will be the condition? Condition will be the load resistance will be equal to the arc Thevenin. So for that case, ZL is my load impedance over here. Load impedance over here, ZL will be equal to the Z Thevenin conjugate. So then the imaginary part will cancel each other. So maximum power will be V Thevenin square over R 8 times R Thevenin. So load resistance will be, amplitude will be this formula Z Thevenin over here. Effective RMS value. RMS is root mean square value. So one is average power, another is the root mean square value. One is average value, another is root mean square value. So for that case, we apply this formula over here, 1 over T, 0 to T, I square R dt for power, for effective RMS power. Then we elaborate these. So R is as a constant, it come out. So then we integrate I square over here. So we get I effective in this format. So V effective will be also in this format. So RMS value of reactance will be in this format. So apparent power is the summation of power, real power and imaginary power. How we are getting imaginary power? We are getting imaginary power from the reactance, the imaginary resistance. So for that case, V equal Vrms times Irms cos theta V minus theta I equal is S. This S is for apparent power, the total power, cos theta V minus theta I. S equal Vrms times Irms, and this is power factor, P over S cos theta V minus theta I. So this is the power factor. Um, so power factor may be negative, positive, maybe zero. So maybe zero. So power factor defines how effective this the circuit will be, how the circuit is close to resonance. If the circuit is resonance, we will get the maximum output from the AC circuit. So when we will get the maximum output when there is no reactance over there. So when I will have no reactance over there, if I have equal amount of reactance of conductor inductor and equal amount of reactance from the capacitor, then two reactance will cancel each other. Then I only left with resistance over there. Then I will get the maximum output from those AC circuit. So complex power or apparent power we can express in this form, in this format, Vrms Irms conjugate. And we can also apply I square R formula over there. So instead of R, we apply Z over here, and Vrms square over Z conjugate. And Q is the power factor or quality factor. When Q equal to 0, that means that load is fully resistive, unity power factor. Q is less than 0, that means the load is capacitive, it's leading power factor. When Q is greater than 0, that's inductive load, it's lagging power factor. So this is up to the AC circuit. Let's talk about the three-phase circuit. So AC circuit, up to now we only talked about single phase circuit. These are only single phase circuit actually. Um, so what will be the case? I have three phase, that means three wire. So I have one sinusoidal over here, another sinusoidal over here, another sinusoidal over here. So these are the three AC voltage wave over here. So for that case, I have three AC voltage source over here. This is the Y connection, and for delta connection, it will be in this fashion. So according to the IEEE convention, so for the positive sequence of A, B, C plus, then VAN. So N is actually the neutral point. So this neutral point is only available for Y network, not for delta network. So there is no neutral point for delta network. And so this is N. So VAN. So phase voltage over here. Phase voltage VAN is plus 120 degree apart from VCL. And VAN is minus 120 degree apart from VBN. So this is for the ABC positive sequence. So for negative sequence of ACV, VAN is plus 120 degree apart from 120 degree apart from VBN, and minus 120 degree apart from VCN. Now, if we want to apply the phase formula in phasor format, so this will be just like this. VPN will be in VN will be in the ground state. Ground state VPN is their amplitude will be same, but 120 degree phase apart. Uh, 120 degree phase apart, and for VCN it will be plus 120 degree phase apart from the VAN. So, and for the this is for the positive sequence, and for the negative sequence, so Vn will be same. Vcn will be minus 120 degree apart from Vn, and Vbn is plus 120 degree plus 120 degree apart from VAN for VBN. So a balanced load is a one in which the phase impedance are equal in magnitude and in phase. So why we are interested in balanced load and balanced load actually, because if these loads are unbalanced, if their amplitude is different, then they will have ringing in the circuit. They will have different voltage amplitude, and ringing will be in the circuit, and actually after some time it will burn the circuit. So that's why the amplitude of the voltage source should be same. So for a balanced Y connected load, so their impedance will be same, and ZY. And if we convert this ZY into Z delta, then 3 times ZY. For balanced YY connection, it will be same. This is the positive sequence and this is the negative sequence. And if we apply in this way, so for the case of VBA, so from voltage from here to here, it will be VAN plus VNB. If we VNV, if we reverse VNB, we get VBN. So this then expression will be just like this, and we apply the rectangular format over here and come up with this root 3 VP in 30 degree apart. So for the case of YY connection, so each phase voltage will be 30 degree apart from each other. So same goes for VBC, same way, root 3 times root 3 times 30 degree apart from the actually the from the phase voltage. So but here it is minus 210. How it is minus 210? Because this is 30 degree apart, minus 180 degree. So that's how it is minus 210. So line voltage will be root 3 times phase voltage. VP will be actually VAN is actually the phase voltage. VAN, VCN, and VVN are actually phase voltage. And for line voltage, it will be VAB, VBC, and VCA. So we get VAB in this way. VN over here, VNB over here, and we get the vector sum of VAB across this diagonal over here. Line current, so this is IA will be in this way. Let's see, where is IA? So IA will be come from here. So IA line current VAN from here to ZL, the ZL over here. ZY, so ZY will be the ZS over here, their impedance are same. That's why ZY. And for the case of IB, VBN over ZY, their all impedance are same. VN, we can also write VBN as VN minus 120 degree phase. Yeah, so we can add I equal minus 120 degree. IC will be equal to VCN over ZY. So it will be minus 240 degree. Why 240 degree? We can write plus 120 degree as minus 240 degree. So, and they are all line current will, if we apply KCL, their sum will be 0. And neutral current also the sum will be 0. So current across this node will be sum will be 0. And also current across this node and this node, voltage across this node and this node will be also 0, because the current will be 0. Why current will be 0? So all current is coming here. So if we apply KCL, this node will be 0 over here. just we apply KCL over here. So what will be the case if we have Y delta balanced Y delta connection? So for that case, we have ZY will be ZS over ZL over ZL and ZL. VAN will be just like this, same thing. So for the case of VBC, so VBC over here, so it will be let's say VBN minus VCN over here. So VBN plus VNC, we can write that minus VCN, and we put the value across there. And VCA will be same, 2-3 times VP in amplitude plus 30-degree phase apart. So VAB is the line voltage across here, which is VAB, this line voltage, capital VAB. So VBC is same, 60-degree apart, and this one is 90-degree apart. And for the case of IAB, let's see, IAB is the line current. So yeah, so line current VAB over Z delta. Z delta is actually the impedance of the delta network over here. In delta network over here. So it will be just like this. Parents Y delta connection. So right here. So yeah, so line current, and this is the load current over here, load 3 times IP, and load current will be equal to IA, IB, and IC, the line current. Okay, and ZY will be as usual, so Z delta over 3. Okay, so what will be the case for delta delta connection? So for delta delta connection, VAV phase voltage will be same, as the positive sequence will be there. So for that delta delta connection, my line voltage and phase voltage will be same. So this is my IAB. So this is my line current, and Z delta. And this is my output, and this is my input over here. So in both cases, they should be same, because maximum power transfer theorem, because their resistance should be same and conjugate. So as they are balanced, their voltage amplitude will be same, and all phase will be in phase. So that's why. So IAB equal VAB, capital VAB over Z delta, V equal V small VAB over Z delta. And line current IA, let's see, this is IA. IA will be equal to IAB minus ICA of over here. Yeah, because yeah, we apply KCL over here in this capital A node. And same goes for IV, and same goes for IC. Just we apply KCL in the nodes, and we will get it. And for the line current, IL will be equal to √3 times the phase current. So what will be the case for delta Y connection for a balanced network? So this part is input, this part is my output. So I have the same phase current in the input side, and I have line current, just like this. So we have to convert it to Y line current by dividing √3 over minus 30 phase. Then VAN will be just like this. Yeah, the neutral current will be, the neutral voltage will be in this way for all the phases. And this is the line current, VP over √3. Why this root 3? 30-degree apart, because this part is my Y network. That's why that's why we have to divide this phase voltage root over 3 and minus 30-degree apart, because we are dividing. So for delta delta transformation, so this is one delta, this is another delta. If we convert this to another delta, so this will be just like this, VAN. Vn equal to Ia Zy Vp over root 3 and minus 30. And so let's talk about power in a balanced system. So this is AN. So AN will be, there's a capital N is the neutral part over here. So almost same as root 2 Vp times cos omega t, Vvn, Vp cos omega. So as this is a positive sequence, so that's why this minus 120 and this is plus 120. So Vcn will be plus 1. So what will be the line current? So same thing. So with phases. So phase power will be just like this, Vp Ip cos theta, and phase reactive power will be just like this with sin theta. What's about apparent power? We can write just this way, Vp Ip, or in rectangular format or conjugate format. What will be the total power then? I have one power in phase A, phase B, phase C. So total will be three times of phase power. As they are balanced network, so their power will be, all phase will be same, times 3. So this will be my total power over here. We can write in the real format. So this will be the real format. And so if we write in the phase format, this will be just like this. If we write in the line voltage format, this will be just like this. And for total reactive power, so this will be same, just in terms of sin theta. So apparent power will be just like this with the angle, and this is the loss, I square R loss over here. And this will be just like this. So Ia is the line current, VAN over ZA. So this is my line current, Ia is going on. So IB, so for IB, the IB is going from here. So this is another line current. What will be IB then? So VVN over ZB. So ZB is this impedance over here. And same goes for IC. So this is the end of three-phase circuit. So let's talk about a little bit about transformer. So inductance. So for inductance, we get it in this way, where E is the flux over here. Flux over here, and we have two inductor over here. These two circuits are close to each other. So if we write in this format, so it's just like this. L di dt. L is the self-inductance actually, and N is the number of turns in the inductor. And total magnetic flux will be phi 11 plus phi 12. V1 will be this, and V2 will be this. And for the case of V1, as these two inductors are close to each other, they will actually affect each other with their self-inductance, and this one will affect this one, and this one will affect this one. So we call this mutual inductance. So it's the same format. So V1 will be N21 d dt of I1. N21 is actually N2 di1 of P12. For the case of V2, M21 dt of I1. And our total magnetic flux will be phi 2 equal to phi 21 plus phi 22. V2 will be equal to this one. If we consider the inductor turns, then it becomes d dt of I, L times d dt of I, and this is this, and so this is our mutual inductance. M is our mutual inductance over here. So for the case of dot convention, when I is entering the dot in both sides, then what will be the total inductance? We have self-inductance of L1, L2 plus 2 times of mutual inductance, because current is entering these two dots at the same time. So when current is entering one dot and exiting another dot, or the dot is in the opposite side of the current, then it will be minus. So we see that these two are coupled circuit, and this one is also a coupled circuit. So what will be the energy in a coupled circuit? So we can write energy equal half Li square, and for the power we can apply VI, P equal VI formula. Then we can elaborate this formula over here with self-inductance and mutual inductance. And for I1, for if we consider mutual inductance, then the current will be I2. And for I2, if we consider mutual inductance, current will be I1. So for the case of P1, it will be just like this, I1. And for the case of V1, we will consider only I1. So for the case of P2, we have to take care of the mutual inductance also. If we come out with the mutual inductance, then we have to consider I1 also. Then we also have to consider the current, I2 current also for that side. And the ultimate expression will be just like this. Mm, So this is the energy expression over here at last. Mm, Half Li square, so with the mutual inductance. So to energy will be W1 plus W2. And we see that actually M112 and M21 is actually the same mutual inductance, because this is for this guy this is M21, and this for this guy it is M12, and the amount of mutual inductance is same, so we can denote that it's equal to M. Okay, so for both coil current enter the dotted terminal, the expression will be energy expression will be just like this. If one current enters one dotted terminal while the other current leaves the other dotted terminal, and then mutual voltage will be negative. So for that case, mutual voltage will be negative over here. So yeah, so for that case, it will be subtraction. Self-inductance of these two minus subtraction of the mutual inductance, or dot convention. So we have another coefficient of coupling, which is called K. K varies from 0 to 1. And this is the expression of K. And this is the expression of mutual inductance with K. And K we can write in this way also, but this will be much better. So what will be the case of if we apply this inductor in a transformer? In a linear transformer. Linear transformer means so their voltage increasing or decreasing linearly. So for that case, this is their voltage with the mutual inductance, and we apply KVL in these two circuit. So this is primary side of the transformer. This is secondary side of the transformer. These two equation. And if we solve for Zn, the input impedance, we come out with this, and this part is the coupling part of the impedance. So this is called the reflected impedance, ZR. ZR is this one. So this impedance is actually reflected from the secondary part of the. So this secondary part of the impedance will be reflected back to the primary part. So if we want to express this in the matrix format for V1 and V2, this will be just like this. For For I1 and I2, this will be just like this. For Y network, this will be just like this. So this is a Y network over here, Y network over here, and I have a transformer over here. So this will be just like this. So for ideal transformer, this is my basic equation. This is my mutual inductance. There is no K over here. Why? Because ideal transformer has the property coils a very large reactance. So L1, L2, M1 will be infinity. Coupling coefficient will be unity. So that's why K1 will be 1. So that's why this K1 is 1 over here. Okay. And primary and secondary coils are lossless. So that means R1, R2 will be equal to 0. That means actually there will be no internal resistance of the primary and secondary part. Primary and secondary part. Okay, so if we apply these three properties for ideal transformer, so voltage will be just like this. V2 over V1 equal to N2 over N1 equal N. For the case of current, it's just the reverse. And we have step down transformer and step up transformer. Step down transformer, the secondary side, the voltage will be less than the primary side, and for step up transformer, the secondary side voltage will be greater than the primary side. Okay, so what about the complex power of a ideal transformer? We can apply this formula over here, V1 I1 conjugate over here, or this formula over here, V2 I2 formula from this formula over here. And for input impedance, we can apply this formula ZL over N square. Z Thevenin will be V1 over I1 because this is the input impedance, primary side impedance over here. Then we elaborate with voltage over here. Okay. So ideal auto transformer is a transformer. It's not so important. So this not so important for this class. So let's look at the three-phase transformer. So for three-phase transformer, so all the formulas will be same as the three-phase. So like this is the apparent power, total apparent power. This is the total power, ST times cos theta. So this is the line voltage, secondary line voltage, and this is the primary line voltage, primary side line voltage times N. We will apply for Y delta connection. So Y delta connection of the transformer. So delta is in the secondary side. So this will be just like this. VLS will be VLP over root 3, and ILS will be root 3 times ILP over N. And for delta Y transform, when Y is in the secondary side, so it will be expression will be just like this. And this is the turning ratio. This is the turning ratio. I is to N is the turning ratio. So we finish out with AC circuit. Now let's talk about op-amp. Op-amp is short of operational amplifier. So why we use op-amp? We use op-amp for amplifying the signal. Op-amp is used as the current source also, and voltage source also. So op-amp is also used as the dependent voltage source, current source also. So this is the symbol of op-amp. So plus V plus V is the DC voltage, positive DC voltage, minus V is the negative DC voltage. I1 negative is the inverting part, inverting point, and plus is the non-inverting part, and this part is the output. And KCL, if we apply KCL in this op-amp, so I0 equal to I1 plus I2, I1 plus I2 plus I plus I minus, this I minus. So differential input voltage VD equal to V2 minus V1. So if we want to get the output voltage, so it will be in this fashion. So A times VD. So VD is the differential input voltage, V2 minus V1. So A is the gain factor over here. So how we get the differential input voltage? We get differential input voltage, the voltage difference between the inverting and non-inverting part. From there, we get the differential input voltage, and from differential input voltage, we get the gain factor. Actually, this is the open loop gain factor, and op-amp work in three regions: plus minus saturation region and linear region. When V0 is positive VCC, then it will be in positive saturation. For linear region, it will the V0, the output voltage will be in between plus minus VCC. And for negative VCC, V0 will be working in the negative saturation. So these are the properties of ideal op-amp. Infinite open loop gain, so A will be infinite input resistance, Ri will be infinite, so Ri, this Ri over here will be infinite actually. For ideal op-amp, zero output resistance. So if we have infinite Ri, then I1 will be 0 and I2 will be 0. I2 will be 0, then voltage difference will be also 0, then V1 equal to V2. So inverting op-amp, how we get inverting op-amp? So when the input is connected with the inverting part, so we get inverting amplifier. So we apply KCL in this circuit. So inverting circuit over here, and it will be just like this. Then V0 is equal to minus RF over R1. That's VI. VI is the input AC signal. And RF over I1 is actually the gain factor over here. So what will be the non-inverting amplifier? So where input is in non-inverting point. So that is the non-inverting amplifier. Then we apply KCL over there. Then our expression, non-inverting expression is just like this. And for the case of voltage follower, so V0 will be equal to VI. And for the case of summing amplifier, for the case of summing amplifier, what we can do is that for inverting or either inverting point or non-inverting point, we can apply multiple input over there, and they will sum up and amplify. So I have I1, I2, I3 over here, which are all input of the inverting part over here. And if we apply KCL over there, then my V0, the output voltage will be just like this. The sum of all signals, actually sum of all input sum of all input from I1, I2, and I3. For the case of difference amplifier, I will have input both in inverting and non-inverting part. So difference amplifier actually amplifies the difference between two inputs. So if we apply KCL over here, so just like this. So V0, this is the non-inverting part, this is the inverting part over there, then V0 is just like this. For R1 over R2, so if we apply this ratio over here, then differential amplifier V0 will be R2 over R1. R2, where is my R2? This is my R2, which is actually the feedback resistance, and this is my R1. And we get this differential amplifier V0. So one more important thing is the cascaded amplifier. So if we want to amplify the signal in several order, then we go for the cascaded amplifier. So multiple op-amp are connected in series. So this one has A1 gain, this one has A2 gain, and this one has A3 gain. So my input AC signal is V1. So from here, my output will V2 will be A1 times V1. For A2, for this op-amp, output V2 will be A2 times V2. And V2 is this A1 times V1. And for this one, V0 will be A3 times V3. V3 is this value, and V2 is this value. So this is cascaded amplifier, very important. So yeah, this is the total summary of the the course E-Tech 340. If you have any question or concern, so please let me know through email. Yeah. So this is the end of the lecture. Thank you.